NENOMATICA, where mathematics meets YouTube excellence. Welcome to our series on exponents and power laws. Let's begin with our introduction to power. Today we'll be learning about the key concepts of exponents and how they work in mathematical expressions. Let's consider the following expression: 2 times 2 times 2 times 2 times 2. To simplify this calculation, we can write this as 2 raised to the power of 5, or 2 to the 5th power. Let's break down what this notation means. We call 2 to the 5th as follows. 2 is the base, and 5 is the exponent or power. The expression 2 to the 5th means we multiply the base, which is 2, by itself 5 times. So it's 2 times 2 times 2 times 2 times 2. Now let's calculate the value. 2 times 2 equals 4. 4 times 2 equals 8. 8 times 2 equals 16. 16 times 2 equals 32. So 2 to the 5th equals 32. Based on our example, let's review the terminology. We read 2 to the 5th as 2 to the power of 5. This means we multiply 2 by itself 5 times. The base, which is 2, is the number being multiplied. The exponent, which is 5, tells us how many times to multiply the base by itself. Let me introduce 2 important mathematical terms from our notation. The number 2 is called the base. The number 5 is called the exponent or the power. Now, let's look at a more formal definition of exponents. If there is a real number and n is an integer, then a raised to the power n is defined as a multiplied by itself n times. In mathematical notation, we write this as a raised to the n equals a times a, and so on, with there appearing n times. Here's an important note to remember. Any real number raised to the power of 1 equals the number itself. For example, a to the power of 1 equals a. Let's consider a practical application of exponents. One of the key uses of exponents is to provide a shorthand notation for repeated multiplication. For instance, if we want to multiply the number 2 by itself 1,000 times, instead of writing out all those multiplications, we can simply write 2 raised to the power of 1,000. This shorthand notation saves space in writing and increases calculation speed. Using exponential notation helps us save space when writing mathematics and also helps us calculate more efficiently. Let's look at our first example. Here we have 2 raised to the 7th power. This can be expanded as 2 multiplied by itself 7 times. This is read as 2 to the power of 7, or simply 2 to the 7th. Our second example is 1 raised to the 5th power. This expands to 1 multiplied by itself 5 times. Since 1 multiplied by itself any number of times remains 1, this expression equals 1. We read this as 1 to the power of 5, or 1 to the 5th. Our third example is more complex. We have the fraction 4/5 raised to the power of 3. This means we multiply the fraction 4/5 by itself 3 times. We read this as 4/5 to the power of 3, or 4/5 cubed. Let's understand the general pattern. When we have a number or expression raised to a power, the exponent tells us how many times to use that number or expression as a factor in multiplication. In each of our examples, we expanded the expression to show the repeated multiplication. When reading exponential expressions, we typically say the base followed by to the power of, and then the exponent. However, there are some special cases. For the exponent 2, we say squared, as in 2 squared. For the exponent 3, we say cubed, as in 2 cubed. For negative exponents, we say to the negative followed by the number. For fractional exponents, we typically convert to root form. Today, we'll work through several examples of calculating with exponents. Let's look at our first example. First, let's calculate 2 to the 4th power. 2 to the 4th means 2 multiplied by itself 4 times. Next, let's calculate 5 squared, which means 5 multiplied by itself twice. Now we can add the results. 16 plus 25 equals 41. Let's move to our second example. Let's calculate 2 cubed first. 2 to the power of 3 means 2 multiplied by itself 3 times. Next, let's calculate 3 squared, which means 3 multiplied by itself twice. Now, we multiply the results. 8 times 9 equals 72. Let's continue with our third example. For 3 cubed, we multiply 3 by itself 3 times. 4 squared. We multiply 4 by itself twice. Now, we subtract 16 from 27, which gives us 11. Let's look at our final example involving division. For 10 cubed, we multiply 10 by itself 3 times. For 5 squared, we multiply 5 by itself twice. Now, we divide 1,000 by 25, which gives us 40. In this video, we've learned how to calculate expressions involving exponents. Remember, when calculating exponents, you multiply the base by itself the number of times indicated by the exponent. Then you perform the arithmetic operations like addition, subtraction, multiplication, or division as needed. We need to calculate the sum of 3 cubed, 4 cubed, and 5 cubed. First, let's compute each term separately. 3 cubed equals 3 times 3 times 3, which is 27. 4 cubed equals 4 times 4 times 4, which is 64. 5 cubed equals 5 times 5 times 5, which is 125. Now we can add these values together. 3 cubed plus 4 cubed plus 5 cubed equals 27 plus 64 plus 125, which gives us 216. Let's move to our next example. Here, we need to calculate 2 to the power of 6 minus 6 squared plus 4 squared. Again, we'll evaluate each term separately. 2 to the power of 6 equals 2 times 2 times 2 times 2 times 2 times 2, which gives us 64. 6 squared equals 6 times 6, which is 36. 4 squared equals 4 times 4, which is 16. Now we combine these values, applying the operations. 2 to the power of 6 minus 6 squared plus 4 squared equals 64 minus 36 plus 16. Calculating this expression, we get 44 as our final answer. Our first example is 2 raised to the power of 5 plus 1/2 raised to the power of 3. We'll start by breaking down this expression. Let's calculate 2 raised to the power of 5 first. This is 2 multiplied by itself 5 times, which equals 32. Now, let's calculate 1/2 raised to the power of 3. This is 1/2 multiplied by itself 3 times, which equals 1/8. Now, we can combine our results to find the sum. We have 32 plus 1/8. To add these terms, we need a common denominator. Let's convert 32 to a fraction with denominator 8. 32 times 8 equals 256. So we have 256 eighths plus 1/8. Adding these fractions gives us 257 eighths. Let's move on to our second example. We have negative 6 squared plus 4 times 3 squared. For this example, let's be careful with the order of operations. Remember to evaluate exponents before applying the negative sign. So negative 6 squared means negative of 6 squared, not negative 6, and then squared. Let's evaluate each part of the expression. 6 squared equals 36, and with the negative sign, we get negative 36. For the second part, 3 squared is 9, and multiplying by 4 gives us 36. Now we can combine these results. We have negative 36 plus 36. These terms add to 0. Let's tackle our third example, which is a more complex fraction. We have negative 2 raised to the 4th power, divided by the square of the sum 3 squared plus 2 squared. Let's start with the numerator, negative 2 raised to the 4th power. When we raise a negative number to an even power, the result is always positive. So negative 2 raised to the 4th power equals 16. Now for the denominator, let's first calculate 3 squared plus 2 squared. 3 squared is 9, and 2 squared is 4. Adding them gives us 13. Now we need to square 13. 13 squared equals 169. Now we can compute the final fraction by dividing 16 by 169. And that concludes our solutions to these 3 exponent expressions. Remember to follow the order of operations carefully and apply the rules of exponents correctly. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.